personally, I use SGD or Atom Optimizer because Atom is converging fast, so I'm just using Atom most of the time. Start with some low-level nets. So depending on your number of features, 120, 150 neurons, and then you have the batch normalization, ReLU activation, and then the dropout. And if it doesn't work for you, keep on adding layers and increase the number of neurons. And then you have, in the end, a very huge network, and your Amazon cost will be very high. So don't go for it. And yeah, now the AutoML challenge. So the automatic machine learning thing that I was discussing, there was an AutoML challenge a couple of years back. I think 1.5 years back or something like that. So these are some of the results using the framework that I showed you just now. So I was competing against the University of Freiburg. I was competing alone. And I used this architecture to get second rank in the final one results. And this was the final round. Also for the GPU track. So I just used the framework, the rules from the framework to win the GPU challenge. So the next use case that I'm going to talk about is clickbait. So it's pretty famous right now. Clickbaits, fake news. So yeah, it's something, bait is something to lure fishers, and some people think that humans are fishers, but we are more intelligent and more dangerous. So clickbaits are like titles which are very interesting. So you have something like 10 things Apple didn't tell you about the new iPhone. Oh, wow. What is it? Or 9 things you must have to be a good data scientist. So these kind of things, and you will like to when you look at these titles, you want to click them. You want to know what's next, what's the content. But you cannot. I mean, you just go on the website and see its BuzzFeed link. Yeah. So how would you distinguish between a clickbait and a non-clickbait content? What do you think here? Which ones are clickbait and which ones are not? It's very difficult, right? Because you don't know the source, where it's coming from. So only 2 of them are clickbait. Not only. So the McDonald's one and the Wendy's one, and other 2 come from trusted news sources like CNN. Some people won't agree. And New York Times, and I mean, they don't post fake news, I mean, no matter what others say. So to summarize clickbaits, interesting, frustrating titles. Very seldomly you get good enough content, and Facebook or Google, they always keep on penalizing the clickbait contents. So like for clickbaits, what I did was like crawl BuzzFeed and ClickHole, New York Times, CNN. So I collected around 10,000 titles, and I just marked BuzzFeed or ClickHole titles as clickbaits and other ones as non-clickbaits, which is not a good idea. Then I use a simple TF-IDF, and that's my favorite, and these parameters, they always work. They just work 99% of the time. So let's look at some of the interesting words of non-clickbaits. So I didn't do any kind of data cleaning. I'm a very, very lazy guy. So yeah, you can see a lot of random crap. And these are non-clickbaits. I should have removed a lot of things. Should have done some cleaning. So yeah, these are some interesting words for the clickbait. So you can see the numbers, 15 or photos or people. Yeah, so all the numbers like X things you didn't know or X things you must do. So before starting with the model building, we must create a validation and training samples. So now it's a very simple thing, but it's a very important step. And what I did was I did a stratified shuffling and split the samples into validation and training set. So yeah, as I said, I tried a very simple TF-IDF, which is logistic regression, and I got a ROC score of 0.983, which is pretty high. So next I tried my favorite gradient boosting library, XGBoost, and I got a bit low, around 0.97, but it's because I didn't do any kind of hyperparameter optimization. So is that it? Like I was like, then I did some model predictions on text like Donald Trump and Barack Obama. I got 80% clickbaits. I was like, oh no, something's wrong. So TF-IDF was unable to capture the meanings. Then I did word2vec. So like, they're generated by shallow neural networks. I think you guys already know about it, and similar words cluster together. So I just applied word2vec sentence to vector on all the titles that I had, and I got something like this. So you can see like good separation between the clickbaits and non-clickbaits. If I apply XGBoost on word2vec features that I have, the raw word2vec features, I get a AUC of 0.981. So the models were easy to train. It was very fast. Reported AUC was also very good. We can see some results here, but so I mean, yeah, it's working fine, not bad. But yeah, you know, if you're asking for espresso or cappuccino, they have similar word2vec vectors. And yeah, so word2vec is not capturing everything. But why are we using only the titles? We want to know if, okay, if there is a title like 10 things Apple didn't tell you about new iPhone, and if the content is justified according to the title, so it's not a clickbait. So in the next part, we can see how this problem can be tackled. And so I started creating the data again. So this time I crawled BuzzFeed, New York Times, Clickhole, Stop Clickbait Official. So Stop Clickbait Official is, what they're doing is they're just marking clickbaits on Facebook. So this time I extracted everything from Facebook. So the data looked something like this. You can see I should not use Excel. So the things that we are interested in is the link name, the type of status, whether it's a link, photo, or video. So I'm only interested in link and the status link. So this time I had much more cleaner data. So after gathering data from Facebook scrapers, I labeled the data from BuzzFeed, Clickhole, Upworthy as clickbaits, and the rest as non-clickbaits. This is some data processing task, so I'm just cleaning up the mess and cleaning the HTML content. And this time, I created a bunch of features. So I went to every website, I crawled every website and found out the length of HTML, how many links are there, how many lists, ordered lists, unordered lists, number of images. So clickbaits have more images. You can also extract many more features, and create very complicated features. But I was just sticking to these ones. So the more features are like H1 text, meta descriptions. So here's some of the code I use for creating different features. So you can see like I'm using Beautiful Soup, which is a Python library, and it's pretty easy to create. These are just one line of code to create these features that I explained in previous slides. So for example, in BuzzFeed, there was always report and issue thanks, these kind of things. And if you're training your model on these kind of text, then it's learning perfectly that it's coming from BuzzFeed. So let's look at some of these features. So I thought the number of lists would be higher for clickbait websites because they have stuff like X things about the new Galaxy phone, but this was the other way around. And when we look at links, we see the number of links in clickbait websites more than non-clickbaits. Pretty obvious. The same is true for number of images. Of course, they use a lot of external and internal images. And there are interactive elements such as buttons. I didn't see much difference in the mean value here. But now, since we are dealing with text data, it's customary to show word clouds. So you have the word clouds for clickbaits and non-clickbaits. Because that time everybody was discussing a lot about Trump, so it appeared a lot. Yeah, so these were my final features, a bunch of features for clickbaits and non-clickbaits. You can see the difference in the values. So we can now dive into the models. So I started with a simple LSTM with 2 dense layers with dropout and batch normalization. This simple network gives an accuracy of 90% on validation set and 88% on the test set that I had. So Prelude is learning the parameter of rectifier adaptively opposed to simple ReLU. That's the difference between Prelude and ReLU, and I use Keras for everything. So you have the embedding layer, then LSTMs, then a couple of dense layers, and then the softmax output for 2 classes, clickbaits and non-clickbaits. So without changing much in previous network, I plugged in the content text features that I explained. So I'm just merging these 2 features by concatenating them, and this instantly gives an improvement of 7% over my benchmark network. The validation accuracy of this network was 97.5%, and the test was 96%. I don't know if anybody is interested in numbers because 78% of the statistics are made on spot. So the drawback of these models is like it takes a lot of time to train. So to tackle this problem, I was learning embeddings from scratch. But then you have the Virtuvec embeddings and Glove embeddings. So I used Glove embeddings. I didn't have to learn the embeddings from scratch with 840 billion words and of 300 dimensions trained on common crawl data. With the Glove embeddings, the training was much faster and the validation accuracy of same model improved to 98%. But I'm still missing some of the features that I have. So when I plugged in the numerical features, the model accuracy improved to 99.6%. And on the validation set and test accuracy was 99.1%. The validation and test accuracy were pretty close to each other, so I was satisfied with the results of the model. So to summarize, these were the results. So what kind of features I used, what kind of models I was using, whether I was using Glove embeddings or not. So I have skipped time distributed dense, TDD plus dense in the slides. We'll come back to that. The next one was like detecting duplicates in Cora. So how many of you use Cora? Everybody. So yeah, when you're in the office and you have nothing to do, Cora is a good. Yeah, so Cora had over 30 million questions as of March. It's a community-driven website, if you don't know. Users ask questions and the community members provide answers. So it's fun when you have a lot of important things to do. As of March, yeah, 30 million questions, and with so many questions, it's obvious that there are going to be a lot of duplicates. So if you follow Kaggle, there was a competition on Kaggle to detect duplicates in Cora questions, but I'm not going to talk about the Kaggle competition. This is something I've done separately. So first public data release was in late January, and these are some of the samples for duplicate questions. So they're asking how does Cora mark questions as needing improvement. So yeah, you can see that there's some noise also. So these are like the actual questions on Cora, and we can now move to see what the data looks like. So the actual data set, it contains 400,000 pairs of questions. The data was extracted by Cora team. It was very skewed, so to decrease the skewness, they corrected it by adding negative questions. And the distributions of labels in the dataset is not the actual distribution they have on Cora website. And there is noise in data, just like the real world data. So this is a snapshot of the data. We have 40% positive and 60% negative samples. So after this, I've moved to some basic analysis. So yeah, I'm calculating the average number of characters and stuff. I don't know what kind of question is that with only one character, just a question mark maybe. These were some of the very basic features that I implemented. Length of questions, difference in two lengths, number of words, number of common words. I'm going to call them feature set 1. So this is FS1, and these can be implemented using pandas, very simple one-liners. Then I move to fuzzy features. This package uses Levenstein distance to calculate the ratio of features, and it's quite fast. It offers many features, but I used only the ones that I have shown here. Similar to the basic features, the fuzzy features are also pretty easy to implement in Python using the pandas apply function. And the next two features are also pretty basic. I mean, TF-IDF, everybody knows. Don't need to explain that. And then we have SVD, latent semantic analysis. So I'm using scikit-learn for this. And the approximate fuzzy features. So like, if you want to know more about it, it's called approximate string matching. So the closeness of a match is often measured in terms of edit distance. So you can have insertion, deletion. These are the primitive operations that you have to insert a new character at a given position, to delete a new particular character, and to substitute or replace a character with a new one. So the third set of features, combination of TF-IDF and SVD. So you have questions, you have the TF-IDF features for both the questions, and you feed it into a machine learning model. The second one is similar, but just the TF-IDF to the machine learning model. And then we have SVD features separately, then combining the TF-IDFs and SVD. And finally, last one, questions concatenated and fed to TF-IDF, followed by SVD decomposition. Then we have word-to-vec features. We should have them, and I was using Google News vectors. It provides very great insights all the time. And this is how I convert from word to vec to sentence to vector. So I'm just normalizing for each and every word that appear. I'm doing the summation and normalization. And now we can build some features based on the sentence to vector features. So the other set of features are word mover distance. So it adapts the earth mover distance to the space of documents. So it's calculating distance between two given texts by the total amount of mass needed to move words from one side to another. So here you can see like these two sentences, document 1 and document 2, have nothing in common. So if you calculate the cosine distance, the cosine distance is going to be 1. So it says that these sentences are not similar, but they are. So cosine distance will fail in this case, and word mover distance works. The next two features were skew of the word-to-vec vectors and kurtosis. I used the Fisher version of that, and yeah, these are the final features I have from word-to-vec feature set 4. So yeah, different distance metrics that I haven't specified in the slides, and then you have skew and kurtosis, and you can simply use SciP to implement them pretty easily. Yeah, so yeah, these are the raw word-to-vec feature set TS&E projections. So you can see somewhere, you can see like Trump and Hillary are together. I don't know where. Was it? Ah, cool. Yeah. And also India and Pakistan are together geographically. Then we have, yeah, the feature snapshot, the different features that I was using. And yeah, that's continued. And then yeah, you have the machine learning models, because once you have the features, you gotta have the machine learning models. So I went with two of my favorites, again, logistic regression and XGBoost. 5-fold cross-validation. The validation was stratified. I'm using accuracy as evaluation metric, because Cora was using, the engineering team of Cora was using accuracy as evaluation metric. And there are also some research papers based on this data, and I wanted to compare my results with these papers, and that's why I was using accuracy for a good comparison. So yeah, there are some, these are the results for the basic features. So you can see like the basic features, fuzzy, word-to-vec, and all other sets combined together gives you an accuracy of 81.4%. But you shouldn't do that, because it takes a lot of memory I mean, there's a lot of features, millions of features, and 400,000 samples. So maybe we can improve the accuracy using some deep learning techniques, but in order to start with that, we can see something like we can see what kind of layers I implemented. I mean, I was using Keras, so it was pretty simple to implement everything. So it's a LSTMs. There are two ways to feed time series data into neural networks. So you can have a network for each and every time step, or you can use a windowed approach. So windowed approach is the LSTMs introduced by Schmidt-Huber in '97. And I used 2 LSTM layers, and it was very hot in my room. I'm also using one-dimensional CNNs. So this is how you implement one-dimensional CNNs. It's a temporal convolution, pretty easy to implement. So X is the input signal, and H is the kernel, and of course Y is the output. Then you have the embedding layers. So you have the word counts, and you want to create embeddings out of them. These are always the first layers in the network. So yeah, it's converting indexes to vectors. And then I was using this time distributed dense layer, so it's a layer available in Keras. I think, yeah, this one. So I think they have changed the name, but I'm not sure right now. So it's a time distributed wrapper. So what it does, it's applying the layer to the dense layer to every temporal slice of the input. So my base of my models was the SNLI model, if you have heard of that. So we have the GLOVE embeddings. So I was using pre-trained GLOVE embeddings. I think I don't have much time left, right? Okay. So I use pre-trained GLOVE embeddings. I will go a bit faster. And this is the SNLI model. So my model was based on this one, but it was a different kind of model. Before training deep nets, we need to tokenize and convert text to sequences. So you can, yeah, I mean, I have to go fast. Okay, so you have to initialize the GLOVE embeddings, which you can do in this way. There's no rocket science here, just loading a file into a dictionary. Then next we create the embedding matrix. It's required for Keras, and this is the final model that I have. And it's huge. So we can look into it by parts. So the first, starting with model 1 and 2, pretty similar to each other. You have the translation layers, non-trainable weights. So weights from embedding matrix from GLOVE initialized vectors. And I'm using some in lambda layer instead of average that was used in SNLI model. And the output is 300 dimensions. Next is one-dimensional CN.